Yeah, so good afternoon, everyone. My name is Amit Kumar Pal, and I'm currently going with the chapter of determinant, like what we did in the last session. So a bit of description about me. So currently, I'm pursuing my undergraduate from IIT Kharagpur, and I'll be continuing the remaining part of determinant that we had left in the last session. So yeah, so I think we had completed almost, let me just see it once again. So yeah, I think we had completed till the exercise 4.3, and we had already gone through the concepts of minor and cofactors. So I hope that is clear to you, and so the remaining part of this chapter would be basically the application of minors and cofactor and some properties of the determinant and so on. So we'll be seeing that, and if I match from the textbook, so yeah, this is exercise 4.3, and after that we have some important concepts like adjoint of matrix and inverse of matrix. Okay, so these are small terms and basically important ones because they are used a lot in this chapter. So if I talk about the adjoint matrix, so for any matrix A, and the adjoint is denoted by basically there is a notation we denote by C matrix. So C matrix is often referred as the adjoint matrix of the given matrix. So this is nothing but, let's say we have some matrix A1, A2, A3, B1, B2, B3, C1, C2, C3. Let this be our A matrix. So how we define the adjoint matrix is that, mm, since we are already familiar with the concepts of cofactor matrix, right? So we know that C1, C2, C3, let's say, mm, okay, uh, for a instance, let's say we don't denote it by capital letters. It's there is another matrix. We are calling this as a, let's say we call it any X matrix. Okay, and its term let's denote by capital letters. Okay, just to distinguish it from the above matrix, let's say this we our another matrix A1, A2, A3, and this be B1, B2, B3, and this be C1, C2, C3. Okay, so this matrix is nothing but A1 here is the cofactor of A1, and capital A2 is the cofactor of A2, and capital A3 is the cofactor of A3, and so on. Okay, so this is basically the cofactor of every terms that are present in the above matrix, right? And if we take the transpose of the given matrix, okay, so you know how do we take the transpose? Basically, our row becomes our column, and our column becomes our row. Okay, so uh, A1, A2, A3, B1, B2, B3, and C1, C2, C3. So this is XT, basically the transpose matrix. So the same matrix is often called as the adjoint matrix of the matrix A. Okay, and this is nothing but adjoint of A. Okay, so this is all about adjoint matrices. So there is nothing new concept, but this is just transpose of the cofactor matrix. Okay, so if you see the examples like 2, 3, 1, 4, etc. So we can form firstly the cofactor matrix, and taking the transpose of the cofactor will have our adjoint matrix. Okay, and there is one important property here is that let's say we multiply these two matrices. Okay, so this is our A into adjoint of A. Okay, so if we multiply these two matrices, okay, so our this row will be multiplied by this column. Okay, so we'll be getting A1 plus A2 plus A3 A3. Okay, and for simplicity, let's write it again for this column also. So A1 B1 plus this is A2 B2 plus A3 B3. Okay, and so on and so on, and there will be other terms as well, and there will be some terms like I equal to z terms. Okay, so if you carefully observe this term, so this is nothing but, you know, from how we calculated the determinant of the matrix. We have this matrix of adjoint. So if you remember the concept of the determinant, then you know that this is nothing but the determinant of the given matrix. Okay, because how we calculated the determinant, basically we multiplied the first term with its cofactor, second terms with its cofactor, and third terms with its cofactor. Okay, so this is nothing but this is a determinant of a. Okay, and you also know that if the cofactor of any row R1, okay, there is another property, that is if the cofactor of CF of Ri is multiplied with, okay, C, let's say cofactor of any row Ri be multiplied with uh, Rj row of matrix A. Okay, so you know that this value is always equal to 0. Okay, when the rows are distinct, means Ri row cofactor is multiplied by Rj values of any matrix A. Okay, so this value is always equal to 0. Okay, this is also one property. Okay, so this value is equal to 0. Okay, simply. So you are seeing this A1, A2, A3 are the cofactor of first row. Okay, whereas B1, B2, B3 is our second row. Okay, so these two are distinct rows. Okay, so this value will be equal to 0. Okay, similarly this value will also be equal to 0, this value is also equal to 0, and again this value. If you will calculate this value, this fill in the blanks. Okay, so how will you get this fill in the blanks? You will multiply this row with this row. Okay, so again this is R2 row and this is a cofactor of R2 rows. Okay, so you are multiplying corresponding rows with this cofactor. Okay, so this will be again delta. Okay, and similarly for this and this will be our delta I. Okay, and if we expand this value again, so if you take delta common from the complete matrix. Okay, so this is delta and this is nothing but 1 0 0 0 1 0 0 0 1. Okay, yeah, so we reach here, and so yeah, this is simply the whole property. If I sum up the complete description in a text form, so the property is here that A into adjoint of A is equal to adjoint of A into A is equal to determinant of A times of I. Okay, and this is actually an important property because a lot of uh, properties are derived from the given result. Okay, so you will have to remember this property actually, at least. And yeah, there is another important concept, that is singular matrix. So this is nothing special, but like if delta equal to 0, then the given matrix is singular matrix. Okay, and apart from that, there are some small properties. So yeah, and if we talk about the determinant of adjoint matrix. Okay, we have already calculated the determinant of our original matrix, that is A. Okay, so since we know that adjoint of A into A is equal to delta times of I. Okay, now if you take determinant to the both the side. Okay, adjoint of A, determinant into determinant of A equals to determinant of this complete matrix. Okay, yeah, so yeah, and here is one thing that is worth to note, is that what is the value of a right hand determinant. Okay, so if you consider this matrix actually. Okay, so this is nothing but this matrix. Okay, determinant of A 0 0, and this is determinant of A 0 0, and this is 0 0 and determinant of A. Okay, and Okay, so this is complete matrix, and its determinant is what is the value of this determinant. Okay, so this is nothing but if you expand along this row, then this will be simply equal to a cube. Okay, determinant of a cube. Okay, so this will be determinant of right hand side. Okay, so if we see, this is adjoint of a into determinant of a equal to determinant of a whole cube. Okay, so if we cancel here -1, so determinant of adjoint of a is basically equal to a square. Okay, and the important thing to note here is that this a square is only for 3 by 3 matrix. Okay, for any n by n matrix, this is basically equal to adjoint of a is equal to determinant of a to the power n minus 1. Okay, because the right hand determinant would be determinant of a to the power n, and if we cancel one determinant from left and right hand side, then we'll get this as our final answer. All right, so this is about the concept of a determinant, and after that, if we move to the our property, that is inverse matrices. Okay, so if I describe about inverse matrix, so firstly it is denoted by matrix A -1, and sometimes it is often referred as matrix A, but this doesn't mean that we are dividing by matrix A, because there is no concept of a division of the matrices. All right, so uh, let's say we are multiplying any two matrix AB, or let's say BA, and we call matrix B as a inverse of matrix A. Okay, B is equal to A inverse. So firstly, A inverse is the denotion for the inverse matrix. So firstly ये समझना जरूरी है कि A inverse कोई ऐसा नहीं है कि हमने 1/A को A inverse बोल दिया है, but A inverse is the denotion for the inverse matrix simply. Okay, so ये कंडीशन कब होगी? B को हम इनवर्स A का इनवर्स कब बोलेंगे? जब AB is equal to BA equal to I. Okay, इन दोनों का मल्टीप्लीकेशन आइडेंटिटी मैट्रिक्स के इक्वल हो जाएगा। ओके, तब हम इसे इनवर्स मैट्रिक्स बोलेंगे। ओके, सो दिस इज द फर्स्ट थिंग, and for the and the condition for the existence of inverse is simply that determinant of A should not be equal to 0. Okay, so that means A should not be singular matrix, or we can say that A should be singular non-singular matrix. Okay, non-singular matrix. Oh, so from the above property, we had derived one important property, that is A into adjoint of A is equal to determinant of A times of identity matrix. Okay, so if we see if we compare this definitions this with something like A into B is equal to identity matrix, so we are seeing that there is a one additional term here, determinant of A. Okay, so what if we divide by this determinant of A in the both the side? Okay, so let's see what we get. So we get A into adjoint of A by determinant of A is equal to I. Okay, and now if we consider this matrix as some B matrix. Okay, so we can see that this is our important form, that is A into B equal to I. Okay, so what do we conclude from here? Okay, we conclude that B is nothing but A inverse actually. B is equal to A inverse, and that is equal to 1 by determinant of A times adjoint of A. Okay, so this gives an important result, that the determinant of any matrix is simply 1 by determinant of A times adjoint of A. Okay, and now this can only exist only if determinant of A is non-zero. Okay, because we are dividing by determinant of A. All right, and division is only possible when this denominator value is non-zero. All right, so that's why we say that for the existence of inverse, the determinant of A should be non-zero. Okay, So this gives an intuition why we need non-similar matrix for the inverse to be exist. Okay, and basically this is the first property that we need to verify before finding the inverse of any matrix. Okay, uh, because there is no mean to find the inverse if the inverse even doesn't exist, or we can say that there is no mean to find the inverse of matrix if the determinant of the matrix is already 0. Okay, so ये बेसिकली एक इम्पॉर्टेंट प्रॉपर्टी है जो आपको फर्स्टली किसी भी क्वेश्चन में वेरीफाई करना पड़ेगा कि इनवर्स फाइंड करने से पहले डिटर्मिनेंट ऑफ ए जीरो तो नहीं है. ओके, सो या, and apart from that there are other small properties like AB inverse is equal to B inverse A inverse. Okay, so this is the case, and apart from that there are some smaller questions like in the equation questions. So we'll be seeing these questions in the exercise part, and before that let's move to our exercise part, and we will solve some questions related to this. Okay, so like in the first question, you have to just verify some results. Okay, so if we talk about exercise, so for this more discussion, let's see our question number second. So this is basically 3 by 3 matrix. So you have to find the adjoint matrix for this question, and also you have to verify the property that is A into adjoint of A is equal to determinant of A times identity matrix. Okay, so firstly let's quickly find the adjoint matrix for our question. So uh, firstly let's write the cofactor matrix, and after that we'll transpose the cofactor matrix to get our adjoint matrix. All right, so if we quickly write the cofactor matrix, so this terms will be 4, and for this term we'll ignore these two terms, and our matrix should be this. Okay, so 2 minus 10, so minus 8 and another minus sign, so this will be 8, and sorry, this will be 2 minus so 10 plus 2 12, so this will be minus 12. Okay, and sorry for the small mistake, it will be 3 here. Okay, it will be 3 minus 12, and this will be 2 plus 3, 0 plus 6. Okay, so this will be 6, and for this term let's cancel these two rows, so this will be our minus 1 and another minus sign, so this will be plus 1, and um, this will be our 5, and this will be our 2, and for the last row this will be our minus 5 minus 6 minus 11. Okay, so this will be minus 11, and for this term we'll ignore these two rows, and 5 minus 4 1, and there is another minus sign, so this will be minus 1, and for the last term our cofactor term would be 3 plus 2 5, and plus sign. Okay, so this will be our cofactor matrix. Okay, so our adjoint would be only transpose of this matrix. Okay, so we need to transpose out this matrix. Okay, so this will be 3 1 minus 11, and this will be minus 12 5 minus 1, and this will be 6 2 5. Okay, so this is finally our cofactor matrix. Okay, this is 6. So this is our adjoint matrix, and after that we just need to verify the property that is A into adjoint of A is determinant of A. Okay, so let's quickly find A into adjoint of A. So this comes out to be 1 2 minus 2 minus 1 3 0 2 5 1, and this will be 3 minus 12 6 1 5 2, and minus 11 minus 1 5. Okay, you have to quickly multiply these two matrices. Okay, so how do we multiply these two matrices? So we take one row and one column and add the multiplied corresponding terms. Okay, so this will be 3 into 1 plus minus 12 into minus 1 plus 6 into 2. Okay, 6 into 2 is 6 into 2 is 12 plus 12 34, 12 plus 12 24 plus 3 is equal to 27. Okay, and if you multiply this and this, so this will be 6 minus 36 plus 30. So this will be 0, and if you multiply these two, so minus 6 plus 6, so this will be 0. And if you multiply these two, so 2, 1 plus 4 minus 5. Okay, so this will again be 0, and if you multiply this and this, so this will be 2 plus 15 plus 10. Okay, so this again will be 27, this will be 0, and this will be minus 11 plus 1 plus 10. Okay, so this will again be 0, and this last term would be 22 plus 5, so this will be 27. Okay, and if you write this matrix simply, so this is 27 times of 100010001. Okay, so this is nothing but 27 times I, and 27 is nothing but determinant of A times I, because if you calculate the determinant, so the determinant of A is 27. Okay, so this is all about the verification of our property. All right, so the remaining question in question number 3 and 4, you have to verify these things in the same way, and like you have to find the adjoint matrix of matrix A, and after that you have to just multiply the two matrices to prove that this result actually holds true. Okay, and if we move to our further questions, like question number, let's say take question number 6. So this says that you have to find the inverse of given matrix, and you have to find only if the inverse exists. Okay, so let's say we take our question -1, question number 6. So this will be -1 -3 5 2. Okay, so firstly we quickly calculate its determinant. So its determinant would be -2 plus 15, so this will be 13. Okay, so this is non-zero, so we can say that its inverse actually exists. Okay, so if we quickly you know that A inverse is equal to 1 by determinant of A times adjoint of A. Okay, and this formula we already know. Okay, so we'll be using the same formula to find our inverse matrix. Okay, so firstly let's quickly write our cofactor matrix. So the cofactor of this term would be 2, and for this would be minus of -3, so this will be 3. For this would be minus of uh, -5, and for this it would be -1. Okay, and if we take transpose of this matrix, so this would be 2 -5 3 -1. Okay, and if we multiply it by 1 by determinant of A, then this would be 1 by 13 times of 2 3 -5 -1. Okay, so this would be A inverse. This would be our final answer for the A inverse. Okay, and you can also verify the result, that is A into A inverse equal to identity matrix. Okay, since we are not asked in this question, so this should be inverse of A, I guess. Yeah, so you can verify the answer once again by calculating on your own, but I think this should be the inverse of A. Okay, and for the next question, let's take our 1 3 by 3 matrix. So for 3 by 3 matrix, let's say our question number 11. So we'll take one question. It involves a bit of matrix. So 1 0 0 0 cos of alpha, and this is the sine of alpha, and this is 0 of sine alpha and minus of cos alpha. Okay. For the remaining question, like question number 8, 9, 10, you have to just repeat the same procedure. That is, you have to find the adjoint matrix like we did in question number 2. So in that way, you have to find the adjoint matrix and also verify that its determinant is not equal to 0. Okay. And after that, you have to simply do 1 by determinant of A times adjoint of A to find its inverse matrix. All right. Yeah. So if we quickly find the determinant of this matrix, so let's expand along this row. So these two terms are 0. So we just need to find the determinant from this term only. So this will be 1 into minus of cos square alpha minus of sin square alpha. Okay. If we take minus common, then this is cos square alpha plus sin square alpha. Okay. And you know that this value is always equal to 1 from the trigonometrics identities. You know this value is plus 1. So this would be finally minus 1. Okay. So this should be determinant of A. Okay. And since it is a non-zero value, so we can say that if inverse can exist. Okay. And quickly let's find our cofactor matrix. So cofactor matrix would be, for this term this would be minus of 1, and for this term this will be simply equal to 0. For this term also this would be 0, and for this term this will again equal to 0, and for this term it would be, for this term we need to ignore these two cells, and remaining would be our cofactor, so minus of cos alpha. And for the A23 our cofactor term would be sin alpha. Okay. And for 3 1 this should be 0, and this should be minus of sin alpha, and this should be cos alpha. Okay. Yeah, so this is our cofactor matrix, and if we take the transpose of this matrix, so this would be minus 1 0 0 0 or minus of cos alpha sin alpha 0 of minus sin alpha, and this should be, so this is our final adjoint matrix. And if we multiply it by 1 by determinant of A, so our final A inverse would be minus 1 into minus 1 0 0 0 0 minus of cos alpha sin alpha minus sin alpha and cos alpha. Okay. So this is our final answer about A inverse. Okay. And for the question number 12, you just have to simply find A inverse and B inverse separately, and you have to verify the property, that is AB inverse is equal to B inverse and A inverse. Okay. So firstly, you will be finding AB matrix, and AB matrix would be 2 by 2 matrix, and after that you will be finding is inverse matrix. Okay. uh, like uh, like how we usually find the inverse of the matrix. So by the same method, you will be calculating the inverse matrix. Okay. And if you see one our equation question that involves some matrix equation, so about our question number 13, so this is A square minus 5A plus 7I equal to 0. Okay. So from this relation you have to find A inverse. Okay. And our A matrix is given as, so if we quickly find its determinant, so its determinant is 6 plus 1 equal to 7. Okay. So we can say that determinant is non-zero, so our inverse actually exists. So since our inverse exists, so if we notice our equation again, so this is a square minus 5a plus 7I is equal to 0. Okay, and if we multiply by a inverse on the both the side, okay, so this is zero matrix. So in the matrix equation, you have to notice that this is not algebraic zero. Okay, this is basically null matrix actually. So null matrix into inverse matrix is equal to 0. Okay, if we multiply a inverse to the both the side, then this would be a into a inverse minus 5 times of a inverse plus 7 times a inverse is equal to 0. Okay, and you know that a into a inverse is equal to identity matrix. Okay, so this reduced to a minus 5 times I plus 7 times a inverse is equal to 0. Okay, this simply gives us 7 times a inverse equal to minus plus of 5 identity minus a. Okay, so a inverse is equal to 1 by 7 times 5I minus a. Okay, so I'll continue from whatever we had left before. So yeah, this is so we derived the a inverse is equal to 1 by 7 times of 5I minus a. Okay, and if we quickly put the values here, so we get a inverse is basically 1 by 7 times of 5005 minus our A matrix is 3 1 minus 1 and this is 2. Okay, and this is 1 by 7 times 5 minus 3 is 2 and 0 minus minus 1 is 1. 0, this is minus 1 and this is 5 minus 2 is 3. Okay, so this is our final A inverse matrix. Okay, this was easy questions. There was not much difficulty. The only trick part was that you have to multiply with A inverse to the both the side to simplify it further actually. Okay. Similarly, for the question number 14, also you are again given a 2 by 2 matrix and you have to find some unknown values. Okay. So you will be approaching with the same method by multiplying A inverse to the both the sides, and once you find A inverse, so the A inverse will be containing some terms of A and B, and in another way of finding A inverse, so this since we are already given A matrix, so we can directly find this A inverse, and by comparing those two result of A inverse, we can find the A and B. All right. So if we see question number 14, so this is A equal to 3, 2, 1, and 1. So if I quickly find this cofactor matrix, so cofactor matrix would be 1, minus 1, minus 2, and 3. Okay, and its transpose would be 1, minus 1, minus 2, and 3. Okay, and its delta value determinant is equal to 3 minus 2, that is 1. Okay, so this is adjoint matrix. Since our determinant value is equal to 1, so this same matrix would be our inverse matrix. Okay, because the 1 by determinant of A is simply equal to 1. Okay, and from the given expression we have A square plus AA plus BI equal to 0. Okay, so if I multiply with A inverse to the both the sides, so I get A inverse A plus AI plus B of A inverse is equal to 0. Okay, and B of A inverse is equal to, this is A matrix, so A matrix is equal to 3 2 1 1 plus A times I is equal to A 0 0 A plus B times of A inverse is equal to B minus 2V minus B plus 3V. Okay, so if I take these three terms, so in a matrix addition, these three will be multiplied all together. Okay, so this result should be equal to 0. So 1 plus 0 minus B equal to 0. So B is equal to 1. Okay, and if I take any other term, let's say we are taking these three terms, so their sum should also be equal to 0 because this whole matrix addition is equal to null matrix. All right. So this is 3 plus A plus B equal to 0. Okay. And B we have already calculated as a 1. So this is 4 plus A equal to 0. So A equal to minus 4. Okay. So this is simply our final result. Okay. And for the question number 15 and 16, you have to verify one algebraic equation that involves matrices, and you have to find A inverse also. Okay. So like if I take question number 16, so this is 2 minus 1, 1 minus 1, 2 minus 1. This is 1 minus 1 and 2. And you have to verify that A cube minus 6A square plus 9A minus 4I is equal to 0. Okay. So we basically find to we all we need is that we have to find matrices like A cube, A square, A, and identity is already known. Okay, so A square is A into A matrix. Okay, so we'll multiply these two matrices. We'll multiply A with itself. So this will be minus 1, 2, minus 1, and this will be 1, minus 1, and 2. And we'll multiply again with itself. Okay, so if we quickly multiply it, then we'll get, so first term would be 4, and this would be minus 3, and this term would be 7. This should be 2. This should be 8. And for the last term, we need to multiply these two. So we get minus 3, and for this 2 plus 1 plus 2. So this is again 5. Oh no. Sorry, I think I've taken the matrix of different question. Let's check our matrix once again. So this 2 minus 1, 1, minus 1, 2, minus 1, 1, minus 1, and 2. Okay, so the matrix is correct. So our terms would be 2 plus 1 plus, so this is 2 into 2, 4 plus 1 plus 1. So this would be 6 actually. I got a small calculation mistake. So we'll calculate it once again. So this is minus 2 plus minus 1. So this should be minus 5, and this should be 5. This should be minus 5, and this should be 1 plus 4 plus 1. So this should be 6, and this should again be minus 5. This is 5 minus 5, and this is 1 plus 1 plus 4. So this is 6. Okay. And this is A square, and for the calculation of A cube, so we'll again multiply A square with A. So this will give us A cube. Okay. So if we calculate A cube, then A cube would be 6 minus 5, 5 minus 5, 6 minus 5. This would be 5 minus 5 and 6. And we'll multiply with A matrix. Okay. 2 minus 1, 1 minus 1, 2 minus 1, and this would be 1 minus 1 and 2. Okay. So if we quickly multiply these two matrices, so we get 6 into 2 is 12 plus 5 plus 5. So this is 22, and this is our minus 21. This is 21, and this should be minus 21. This is 22. This is minus 21. We all are getting repeating values because here the values are repeating. Actually, if you carefully observe, this is actually symmetric matrix. Okay, because this value is equal to this value is this equal to this value, and this value is equal to this value. So this is actually symmetric matrix, so our final matrix would also be actually symmetric matrix. Okay, so this would be 21 minus 21, and this would be 22. So now we have obtained all the terms, and all we need is just to put the values. Okay, so we'll put the values, and there are also some constant terms that are multiplied, like we have to find a cube minus 6a square plus 9a minus 4 times I equal to 0. So this would be 22 minus 21, 21 minus 21, 22 minus 21, 21 minus 21, 22, and minus 6 times of a square would be minus 6 times 6 minus 5, 5 minus 5, 6 minus 5, and this would be 5 minus 5 and 6. Okay, plus 9 times of a matrix. A would be 2 minus 1, 1 minus 1, 2, 1, 1 minus 1, 2, minus 4 times I matrix. 1 0 0 0 1 0 0 0 1. Okay, and if we add all these terms, so this would be like, if we take first term, so this would be 22 minus 36 plus 18 plus 4. Okay, so this would be 22 plus 24, 22 plus 4 is 26 plus 18 is 40. This is minus times of 4i, so this would be 18 minus 4 is 14, and 22 minus 36 is minus 14. So this should be our 0, and similarly rest of the terms should also be equal to 0. So by this approach we can verify our result, and to find the A inverse matrix, all we have to do is multiply by A inverse to the both the side. Okay, so we get a square minus 6a plus 9i minus 4 times A inverse is equal to 0. Okay, so A inverse is equal to 1 by 4 times a square minus 6a plus 9i equal. Okay, so by putting the values of a square and a in the given matrix, you can simply calculate the A inverse. Okay, we have already obtained a square matrix and a matrix in the above part, so all you have to do is just put the values and do simple addition. Okay, and for the question number 17, you have to find the determinant of adjoint of A for 3 by 3 matrix. Okay, so like we have already derived in the starting of the adjoint part of the determinant, so we had obtained that determinant of adjoint of A is equal to determinant of A square. In fact, we have derived this result for any general n by n matrix. Okay, so for n by n matrix, the result was determinant of A to the power n minus 1. Okay, so we can simply put n equal to 3 in that equation as well, so this should also give A square. Okay, and if we talk about question number 18, so it is given that A matrix is invertible. That means its inverse actually exists. Okay, so you have to find the determinant of A inverse. Okay, so you know that A into A inverse is the identity matrix. Okay, so if you take determinant on the both the side, then this should be determinant of A into determinant of A inverse is equal to 1, because determinant of identity matrix is 1. Okay, so from here the determinant of A inverse is equal to 1 by determinant of A. Okay, this is our result. So in the next part we have some application of a determinant basically, and the important application of the determinant is in the solving of a linear equation. So So you have already solved the linear equation in two variable or three variable in the previous classes. So the basic method was the elimination method where we used to eliminate the variable and substitute its value in other equations. So in like if we had a three variable, then we were given three equations, and from the two equation we would use to substitute the values in the third equation, and finally we'll use to get one equation in a one variable. So that was the basic approach, but here, since we have already studied the concept of matrix and determinant, so we'll be using that concept how we can solve the linear equation. Okay. So the general idea is that let's say our equation is something like a1 x1 plus a2 x2 plus an xn equal to b1. Okay, where x1 x2 xn are some variable and a1 a2 an are coefficients. Okay, so let's say we are given some m equations. Okay, so this would be something like for the simplicity to differentiate the variable, let's say this is a 1 1 1 2, this is a 1 8 n. Okay, and in the final mth rows our terms would be a m1 x1 plus a m2 x2 plus a mn xn is equal to bm. Okay, and if we simply represent this in a matrix form, then this equation is simply a11, a12, a13, a1m, and this is am1, am2, amn. Okay, this is n. Okay, and if we multiply this by x1, x2, x3 up to xn. Okay, and this would be something like b1, b2, bm. Okay, so firstly, let's check our consistency of this equation. Like this is m by n matrix. Okay, and this is n by 1 matrix. Okay, so if we multiply the matrix of these two dimensions, then we will get m into 1 matrix. Okay, and this is indeed our m into 1 matrix. Okay, so here these are our variables and these are coefficients. Okay, and depending on the condition of this matrix, uh, whether we are depending on the number of m, like number of equations or number of variables, and also the type of this matrix, so we can conclude different result, what can be the type of our solution. Okay, so in general case, in a specific case, we are given n equations and n unknowns. Okay, so like this is our perfect n by n square matrix. Okay, but like if you will study further in a classes, this might not be always the case that you will be given all the equations. Okay, you might be given some less equations or more equations. So but the specific case is that you will be given equal number of equations and unknown, so this will be our perfect matrix. Okay, so if we represent this matrix in our equation form, then this is simply equal to a into x is equal to b matrix. Okay, where our a matrix is a matrix of coefficients a1 a2 an, and x is matrix of coefficient unknown terms like x1 x2 xn, and b is our constant terms b1 b2 up to bm. Okay, so you have to find the x matrix. Okay, so one thing you can do, you can multiply by a inverse to the both the side, then you will get x equal to a inverse b, and a inverse is equal to 1 by determinant of a times adjoint of a times of b. Okay, so this is direct result, but a lot of caution are required while doing this. Okay, because we don't know what is the type of matrix A. Okay, the matrix A might not be invertible. always. Okay, let's say we have determinant of A is not equal to 0. Okay, in that case, if our equation is n by n perfect square matrix, then we can find its inverse actually. Okay, and if we can find the inverse of this matrix, then definitely we can also find the unknown terms. Okay, we just have to multiply A inverse on the both the side, and we'll get our unknown matrix. Okay, so this is case when we'll get unique solution. Okay, and next we come across the case that is determinant of A is equal to 0. Okay, in that case, you know that you can't do this procedure actually. You can't move from to the next step. You cannot multiply with A inverse. Okay, because A inverse does not exist. Okay, so what we are going to do actually? So in that case, actually, we have our choices like you'll study here, then this system may or may not have solution. Okay, and for the condition to exist, let's say our determinant is 0, and if our adjoint of A is also equal to 0. Okay, so in that case we can say that a solution will exist and there will be infinitely many solutions. Okay, this infinitely many solution would be just because our some equation would be overlapping equation, like they might be of form like 2x plus 3y equal to 6, and another equation might be, let's say, x, let's say this would be 4x plus 6y equal to 2 or 12. So the equation might be of this form, so you know that these two equations basically represent the same equation. Okay, so there might be infinitely many solutions for this equation. Okay, and there is second case also, like if determinant of A is equal to 0 but adjoint of A is not equal to 0, in that case we can say that there won't be any solution actually. Okay, so we won't be getting any solution. Okay, so this is the description about theory of the equation. So you just have to verify these result at every step. Like firstly you need to verify if the determinant is 0 or not. Okay, if the determinant is 0, then you will move to the next step, that is verifying whether the adjoint of A is 0 or non-zero. Okay, so this is about the theory part of this uh, matrix equation system, and lesson part will be solving the question related to this concept in the next lesson, and we'll also be solving some better questions that are asked in the miscellaneous examples and miscellaneous exercise. So they basically contain some better questions. So we'll be solving these two part in the next session. So bye for the today's session. This is all about the today's session, and I think we have covered the theory part almost, and we are just left with solving the few questions. Okay, so we'll be seeing those in our next session. So have a good day, and see you in the next session.